In this series, we will explore the groundbreaking evolution of artificial intelligence architectures, starting with the basics of CNNs, the backbone of image recognition, and then leading up to revolutionary transformer architecture. It's all started in the year 2017 with a paper called as All You Need Is Attention. And as you can see, it has now evolved into a lot of LLMs at this point of time. At the core of this is CNNs, and it is very much important to understand the basics of how CNNs work before we get into LLMs and its applications. So let's proceed with the basic concepts that power CNN. In this video, let's see how our brain sees an image. If I were to show you this image and ask you if this is a panda or not, what would be your answer? It can be a panda for people who are looking at this for the first time. It may not be a panda, it might be an unknown animal, but since we are trained on this image, how does our brain perceive this? It starts from the smaller sections of the image or smaller sections of data. So you look at it and you say that, okay, this is an ear of a panda, these are eyes, this is a nose, these are hands, and these are legs. And now when you combine the ears, eyes, and nose of a panda, you typically get a head. Similarly, you club hands and legs together and you identify if it's a body or not. And when you look at it as a whole, you define if it's a panda or not. So if you look at this construct, smaller elements of data are combined together and a decision is made, and then again it's constructed to define if it's a panda or not. That's how our brain works. Now let's see, if I wanted to map it in a 3x3 matrix or some matrix kind of a element, how would I do that? So if I only wanted to detect the eyes of a panda here, how would I do it? So typically the eyes would come here and here, right? That's a ballpark estimation of where the eyes would be. So I'm marking it as 1 and 1, and the rest are typically zeros because that's where my eyes is. And what am I doing? I'm only using an eye filter to detect an eye of the panda. Similarly, if I look at the other image, there is an eye filter, the same eye filter, which goes through this image and then figures out where the eyes are. So if you look at it in this, the eyes would be on the bottom right because the panda is sleeping. Now, this is like you took a filter, you applied on an image to detect a feature of an image. The feature was eyes, right? If you go to this image, now I club more filters, right? It can be an eyes filter, it can be a nose filter, it can be ears filter, it can be a hands filter, and it can be a legs filter. So remember the image that I showed you before about how a human would perceive? Now, if the computer or an algorithm would want to define this, these filters would actually go through this image, identify where the features are, and it would plot it on a particular box or something called as channel. So we'll come to that in the concepts part, but it is called a channel. So the eyes or the eye feature filter actually takes out the eyes, puts it in a box. The nose filter takes out the nose, position of the nose, spatial dimensions of the nose, puts it in a box. The hands puts it in a box, and that's called as feature extraction. We have extracted a feature. Then you combine again, you aggregate both these things to figure out where the head is. You aggregate these two things to figure out where the body is, right? There are a lot of other concepts that we don't have to worry about right now. So let's look at the main concepts in CNNs. This is the first concept that I want to talk about, and it's called as convolution. If you can see, there is a patch which is going through an image, and this is an image of a cat. It is going through an image. It is going from top left to bottom right, and this is how typically camera shutters also work. So when it is going from left to right and top to bottom, it's called as convolving. So basically the patch that you see here is called as a kernel. So a kernel is typically of size 3x3. And why 3x3 and not 4x4 or 5x5 is something that we can maybe discuss in a later series. But a kernel of 3x3 is convolving on an image which is 1, 2, 3, 4, 5, 6, 7 by 7. Right? This is called as convolution. So when a kernel, so this patch that you see is called as the kernel. This is convolving on a larger input size image of 7 by 7. So it picks up 3 by 3 from here, and then the output is 1 pixel. So let's look at concept 2, which is kernels, channels, and strides. A kernel is called as a filter or a feature extractor. So the dark space that you see here is called a kernel, and it's optimized to a 3 by 3 matrix, which is convolving on a 5 by 5 matrix here, right? Its duty is to identify and extract features and put it in channel. Then what is a channel? The channel is a feature map which identifies the spatial dimension of that feature. So where that feature was located in a particular image. So that's called as a channel. And what is a stride? A stride is the steps that the kernel is taking while it is convolving here. So if you can see, it's taking a stride of 1 here. It's going 1 step at a time, right? So what are kernels? Kernels are filters which picks up a panda's eye or ear, takes it out, puts it into a channel. Each channel is associated with one feature. So one channel for panda's ear, one channel for panda's eyes, one channel for panda's nose. And strides are the steps that the kernel is taking to convolute on the input image. Now let's go to receptive field. This is the most important topic of CNN. It needs to be understood very clearly. So what's our textbook definition of receptive field? Receptive field of a CNN or a convolutional network refers to the region in the input space. So if you look at the region in this input space, the receptive field for this layer is 3. The receptive field for this layer is 1 because every pixel knows about it if it is looking at itself. So the receptive field for this layer is 1. The receptive field here is 3 because every pixel here is looking at the input space region of 3 pixels at a time. And what is the receptive field of this layer? The receptive field would be 5 because it's looking at this 3 plus this extra 2, right? So that's called as the receptive field, and this is a very important concept in CNNs that would be covered in later series. Okay, the last concept for this video is called as padding, and why is padding important? Padding, by definition, in CNNs are used to preserve the spatial dimensions of the input through convolutional neural networks or through layers. So if you look at it, this is a standard image, a kernel which is convolving on an input of size 5 by 5 without padding. So if you look at it, it convolves on a 5 by 5 to give you a 3 by 3 because some pixels are reduced. Now, if you want to preserve the spatial dimensions, and that's where padding comes in. So if you want to preserve the spatial dimension of an image, what you do is you put a padding of 1 pixel around that image. So now this image 5 by 5 becomes 7 by 7 here, right? When you convolve a 3 by 3 matrix on a 7 by 7, what do you get? You get a 5 by 5. So you get the same image back again. So did you lose any pixels there? No. So this is one technique which is used to preserve the spatial dimensions of an image. So just to recap, we did the 4 concepts in this video lecture. First, we spoke about convolutions. Then we spoke about kernels, channels, and strides and their effects on convolutions. We spoke about receptive field, and at the last, we spoke about padding. Please do revise these concepts for better understanding of CNNs, as these are the basic building blocks and more to come, which would actually help you build good CNN architectures.